So yeah, I wanted to talk to you today about what I've been working on for my Blue Waters Fellowship this past year. So this is a slight departure from what I've done for my thesis work, but builds quite substantially, I think, in enabling astrophysics and enabling some of the work I've been doing in galaxy scale simulations for sort of the next generation HPC systems. And this is work done predominantly by many other people for many other years, and I've sort of tagged along this past year to sort of add in extra capabilities to the Enzo-E project. So in general, over the past few decades, progress in astrophysical hydrodynamic simulations, and particularly those that simulate galaxy formation and galaxy evolution, have made substantial improvements in their ability to simulate realistic galaxies and realistic galaxy properties, and due to a large part just to general advancements in more powerful HPC systems. So just being able to add more processors to your simulation allows you to capture greater dynamic range in the simulation, which enables you to sort of better account for a greater variety and more detailed physical processes that govern galactic evolution. And I think one of the key processes here that's sort of really enabled a lot of the advancement over the past decade or so has been a more careful understanding and more detailed approach to understanding what's called feedback physics. And this is the sort of the effect of stellar winds and stellar radiation and supernovae, and as Tom just talked about, black holes and AGN, and how those different processes sort of regulate star formation in galaxies and drive outflows and galactic winds in galaxies. And this is true for sort of regardless of what simulation code that you're using. And so this image kind of shows a good example of multiple different cases of cosmological simulations of galaxies by many different authors that have made sort of strides in this regime. And that's independent of method. There's Lagrangian methods which follow hydrodynamics through SPH, or sort of moving mesh methods. There's Eulerian grid-based codes, and then there's also sort of hybrid meshless codes. And so rather than giving an overview of all these different codes, I'm just going to talk about one that's sort of relevant for what I've been doing in my project, and that's Enzo. So Enzo, and you can go to the website here, is an adaptive mesh refinement grid-based code that sort of used predominantly for sort of galaxy scale physics and cosmological simulations, but has been applied for a variety of contexts in astronomy and astrophysics. It was originally written back in the sort of early 90s in C and Fortran, has been built up over the intervening few decades into sort of a large community code that's open source and used by many people and many researchers across many institutions. And so the physics that's included in this, there's everything. So there's multiple hydro solvers. There's MHD physics. You can account for cosmic arrays, star formation, stellar feedback. There's a ray tracing radio transfer solver in here. And you can do a lot of fun cosmological simulations. There's gravity for both the baryons and the dark matter. It allows us to follow particles for the stars and also the dark matter. It's coupled to various radiative heating and cooling models, and also various chemistry models. And so that allows you to do, and also in addition to all that, it's an open source code, like I said. And so both the development branch of this code itself and the stable branch are open source, and you can go to GitHub and download it and play around with it as much as you want. And what this allows you to do is sort of do simulations which may look familiar to what you saw yesterday. So this simulation of a Milky Way galaxy that you saw in the movie yesterday was made as a simulation from Enzo. And you could see clearly, this produces especially if you post-process it extensively, produces quite exquisite simulations. And so you can see this is the evolution of the Milky Way galaxy. You can see the cold gas sort of moving around the galaxy, the stars forming and exploding as supernovae, and you can see some of the sort of the hot gas and the metals getting ejected from the supernovae and involving the galaxy as sort of the red shaded regions here. And so while you can do quite impressive things with Enzo itself, there are significant challenges in using a code like this, which was designed 20 plus years ago in the next generation systems. And in particular, so Enzo and other codes like it sort of have problems and shortcomings for scaling to systems where you want much more than 10,000 cores. And these are the exascale systems in the next generation that we want to try and target. And some of the restrictions, a lot of the major restrictions and challenges here is that it comes in both terms of load balancing limitations and just how the code is designed in the first place. It's not designed to sort of scale to these kinds of systems. And there's a lot of significant memory overhead in, again, the way the code is designed and the way the AMR hierarchy and architecture works in this code that prevents you from sort of scaling to these kinds of systems. And finally, as I think if you went to Forrest's talk yesterday, you sort of recognize that Enzo itself has limited, if any, utilization of GPUs, and sort of these kinds of codes that are hybrid and can account for both CPU and GPU acceleration is sort of would lead to pretty dramatic improvements in speed, and also is something that's completely necessary in certain systems where a lot of the computing power is placed on the GPUs. And so in order to really make strides and advancements in all these categories, you can make improvements by just sort of modifying the code slightly, but really you need sort of a complete overhaul of the entire code in order to sort of leverage large exascale systems. And to give you sort of an overview of maybe some of the changes that have been done and need to be done, I'll give you some technical details of Enzo itself. So Enzo is a patch-based structured AMR code, and you could see sort of an example of what the grid structure looks like in Enzo on the right. And so Enzo itself is a patch-based with an unbalanced mesh, and so what that means is that each sort of grid in Enzo can be roughly arbitrary size. They're all rectangular and they're all static and they don't move around necessarily, but the sizes of the grids themselves can be played with depending on need in the simulation. And that's kind of nice because it reduces maybe some memory overhead. You only really refine exactly where you need to. But that really complicates communication and load balancing and entails a lot of sort of memory overhead and sort of understanding exactly the global scope of all the grids across all the processors. And so Enzo itself also uses MPI communication, as do many codes, to handle communication across processors. And it has sort of hybrid particle mesh methods to sort of simulate both particles like the dark matter and the stars, and the hydrodynamics and the baryons themselves. And so again, the shortcomings here are sort of, one of the largest is that Enzo right now sort of replicates the entire grid hierarchy across all MPI processors. So each processor knows everything about the full simulation domain, which simplifies some things, but is extremely memory intensive. And so especially if you're running on certain nodes with you might have nodes with a lot of processors, but not a lot or huge memory per processor count, and so it really inhibits you in trying to scale up to very, very large simulations where you could easily overwhelm the sort of the node, the total memory on the node just by keeping track of the whole hierarchy itself. And like I said, the patch-based AMR is nice in some regards, but it's difficult to load balance properly and efficiently. And there's sort of overheads in how sort of each parent and child layer, so each of the lower refined and higher refined levels communicate with each other and are structured. There's some overhead there. And there's interpolation required in those sort of parent and child level grid cells. And evolution itself, just the way Enzo is constructed, is sort of occurs level by level across the entire computational domain. So one level of the simulation must complete its computation before it can be done on the next level itself. And so what that reduces the amount of sort of asynchronicity that you can achieve in these kinds of simulations. And so with that in mind, with those sort of shortcomings in mind, a while ago, if you went to sort of Mike Norman's talk yesterday, you have a much better overview of the Enzo-E project. But the Enzo-E project the Enzo-E/Cello project was designed in the first place to sort of target these shortcomings and rewrite a scalable AMR hierarchy and Astrophysical hydrodynamics code from scratch to target these exascale systems. So Enzo-E and Cello itself are also open source, and they're on the sort of the same GitHub project repository, so you can also download these codes and play with them themselves. And some of the, some of the main advancements in Cello, to give you an overview of what these two things are. So Cello itself is what controls the hierarchy and the parallelization. And it controls sort of the interactions with Charm++, which I'll talk a little bit more about in a second. And it provides sort of easy APIs to layer on your own physics modules, which is sort of the Enzo layer. So in principle, you could take the Cello layer independently and add in your own hydrodynamic solvers, your own physics, and everything like that. But the Enzo layer or the Enzo-E layer is what controls sort of what physics actually happens on each individual block in the simulation. And so some of the key differences with Enzo-E and the Cello project is that rather than having sort of an unstructured patch-based AMR, this is an octree space AMR with a balanced mesh. And so what that means is that all the grid cells or all the blocks themselves are the same size. And all the blocks themselves force sort of a 2-to-1 refinement criterion between levels. And you can see that creates sort of a much more regularized refinement structure in the actual simulation and allows for a much more efficient load balancing scheme. And much better sort of memory management across the whole simulation domain and across all processors. And one of the other key differences that sort of enables a lot of this improvement in load balancing and memory management is that rather than using MPI for communication, Enzo-E and Cello uses Charm++ for parallelization. And what that enables you to do is, as has been talked about in Tom's talk, is more task-based parallelism where each block in the simulation is its own task and can run independently and asynchronously with the rest of the simulation domain. And it allows for sort of, again, asynchronous execution and automatic load balancing across the entire simulation. And what that allows you to do is it sort of gets rid of some large limitations with Enzo itself. And so the entire hierarchy is localized across each processor or across each block. So each block just knows about itself and its neighboring blocks and doesn't need to know about the entire domain, and it allows you to scale up to much larger simulations without sort of overloading the memory limits on a node. And then again, yeah, Charm++ provides significant advantages. And so this is a couple plots that Mike showed yesterday in his talk with much better movies, but I will sort of regurgitate them here. So the Enzo-E and Cello project has been designed, again, for the past several years, and over that time, it's demonstrated some pretty impressive scaling results. So this is the movie that Mike showed yesterday, which is individual sort of letter-based explosions happening across many different processors, run on 256,000 cores, which entails a large number of grid cells and a large number of blocks. And this is a kind of simulation that would be completely impossible to do with Enzo itself, just for memory management reasons alone, let alone actually achieving proper scaling. And as Mike showed yesterday, the scaling results with this are actually quite phenomenal. So if you just look at the top line, that's again just the scaling. The amount of time spent on just the computation itself of the physics dominates, and really the communication and then managing the hierarchy in itself is actually subdominant across the whole simulation, regardless of the number of cores that you're running on. And so it's now at the point where Enzo-E and Cello is capable of doing a lot of cool, interesting science. And so the last sort of remaining piece to get to that stage is to layering on the physics modules in the Enzo-E layer to be able to run sort of production science level runs. And so as a Blue Waters Fellow, that's what I've been doing over the past year, and that's sort of layering on a lot of the physics methods that were implemented in Enzo itself into Enzo-E and Cello. And so it includes coupling Enzo-E with gas cooling and heating and non-equilibrium chemistry model, which is called Grackle, including sort of a model for sort of background acceleration if you want to run a simulation of, let's say, an isolated galaxy but didn't want to care about dark matter particles, for example. Algorithms for star formation, algorithms for stellar feedback, including predominantly the effects of supernovae, and sort of an initial condition generator for isolated galaxy simulations. And my goal as a Blue Waters Fellow was to sort of target to create a sort of Enzo-E version of that movie that you just saw earlier, of that Milky Way mass galaxy, and to try and target just initially that simulation exactly as is, and then to see how much greater resolution we can achieve and what kind of scaling properties we can achieve with the simulation. And so unfortunately, I don't have those results yet, and so we're still working on, so all these physics methods have been implemented, and we just have a final couple loose ends, which Mike talked about yesterday with the gravity solver, which have now been fixed, and a couple other things that are sort of the last remaining things to do before being able to do these kinds of simulation, which I'm hoping to be able to do by the end of the summer. And so in addition to sort of that work, which will allow for, again, these sort of isolated galaxy simulations and also enable cosmological simulations of galaxy evolution, there's work being done to sort of implement flux correction across these simulations, improve sort of the stellar feedback algorithms from sort of the simple thing that I've implemented to sort of more modern feedback algorithms, which have been used extensively in other cosmological simulations. And also there's work ongoing and sort of nearly complete to add in full MHD solvers with cosmic ray feedback in physics, to add in ray tracing radio transfer ported over from the way it's been done in Enzo itself, and to also allow for sort of block adaptive time stepping, which would really allow for better and more impressive scaling properties of the simulation. Thank you.